And we would now like to move on to the next talk from the University of Newcastle, Ben Vaughan. Now, Ben gives really good presentations. He'll be talking to us about pushing roll-to-roll printed solar panels to the market. Ben, I must warn you, we have investors in the room. Good luck.
Thanks, Marius. I always like talking to people with money, so do you want to? Hi, everybody. Firstly, just checking everyone can hear me okay. Just a thumbs up or a... Yep, perfect. Okay, fantastic. So I'm coming to you today from our pilot scale print facility at the University of Newcastle in the Centre for Organic Electronics, where we make printed solar cells. Now, what is a printed solar cell? Well, I'm holding one here in my hands. It is a lightweight, flexible device that converts sunlight into electricity. It's a little different to your typical silicon-based photovoltaic. It's extremely lightweight, flexible, and portable. So today, I'm going to give you a little bit of an overview of some of the projects, some of the companies we've been working with, and a little bit about the pathway towards commercialization of this technology. Also, I'll give you a little bit of a tour of our facility so you can see some of the equipment and perhaps hear about some of the other things that we do. So the first thing I'll do is walk through how we make these, and what you're seeing now is a video of our print line actually running. I couldn't run it today, it's too noisy. But what you're seeing now is a silver layer being printed. Most of these devices have silver or aluminium electrodes in them. We then have polymer layers. Most of the devices we make are made up of a stack of different layers of different polymers, conducting polymers that can convert sunlight into electricity. And all of these are put down with roll-to-roll printing techniques. So then the final layer in most of the devices is a metallization layer. So it's a sputter-coated aluminium. And then at the end, because we're going to put them out in the environment, we encapsulate the solar panels in a barrier film, which gives them the lifetime that they have. And then once you've done all that, you end up with one of these devices that I'm holding here. So the tools that we're using, such as the one you can see behind me here, so this is a roll-to-roll converting line. They're normally used for things that are a bit more basic. So stickers, wine bottle labels, CD labels, these kinds of things. These are very common industry tools, and what we're doing is pushing them to produce functional devices. So typically printing, you want to make something that looks good. You just care about how it looks, its visual appeal. In all of the devices and activities that we're doing, we actually care about the function of the layers. So whilst they may look good, the actual interest is in the function of the layer itself. So that's why we call it functional printing. It's called roll-to-roll for obvious reasons. Everything starts on a roll and finishes on a roll, and we do some kind of processing in between. The final layer over here, we use a roll-to-roll sputter coater, which at the moment is down, just looks like a big dome. That is where we do our metallization. We have a new tool coming next year that will allow us to run much faster, do more interesting materials, some silicon dioxides and a few other things to be able to look at barrier film. But all of these materials are printed here in this facility for these devices. So the various layers are extremely thin, and that's what drives the economics of this product. That's why people are interested in it. The overall, if you look at a cross section of the device, about 95% of it, 97% of it is actually the plastic it's printed on, which is about 75, 80 microns thick on a couple of layers. And then all of the layers that we're actually printing are only a few hundred nanometers thick. So there's not a great deal of material there, which means we can cover vast areas with this technology. The overall efficiency of these solar cells is low compared to traditional silicon. The lifetime is short. However, the cost of the energy produced is very low. It's very competitive with silicon. And as we move into the higher performance materials, it starts to become competitive with other non-renewable energy generation techniques. So if we look at some of the projects that we've been doing with this, 2018, we put a couple of 100 square meters on the roof of a building out at Beresfield. So a company called CHEP, who do pallets, they're owned by Brambles. They have a pallet reconditioning facility out there. And we put 200 square meters on their roof. That project was really looking at how we actually stick this to the roof. We've been working with various companies over the last 20 years to develop this technology, and now we're starting to get into the application. How do we actually roll this out into a functioning device that's in the community? It turns out that the best way to stick it to a commercial roof is with double-sided sticky tape. That sounds a bit silly, but I can tell you that that stuff has been on that roof for 3 years now, and we haven't had a failure, and we've had a lot of weather roll through there. So one of the advantages of this technology, the fact that it is so light, it means that your balance of system, the framework that you need to hold it onto a roof is very, very simple. It's very cheap, because it would be rather pointless to make a very cheap solar panel, which you then have to spend a lot of money on the framework to put it on a roof. Then last year, 2020, aside from being stuck at home a bit, as we all were, we managed to get a set of these panels in a park. It's called the Canopy. It's at Lane Cove. So if anybody is in Sydney or going to Sydney, you can go and check these out. So the park is on top of a new car park that some supermarkets put in. It's a lovely park, and we've got a kids' playground there. And we've actually incorporated the panels into an arbor there, a walkway, and it powers a light display that has colored lights that are activated by people walking underneath them. We actually had our millionth activation the other day. So it was another project, a demonstrator project, the same as the CHEP one, where we're looking at the application of the technology rather than the development of the technology. So you'll start to see a theme in the things that we're doing. We're doing projects that start to look at different components of how we actually implement this technology into the community. So then this year and next year, what we're focused on is what's called Charge Around Australia. We've partnered with a company in the United Kingdom, and they are going to be driving a Tesla around Australia, so complete circumnavigation of Australia, and we'll be charging that vehicle from some of this printed solar out in the more remote and regional areas where charging infrastructure is not as yet available. So the Tesla will be carrying some of that solar in the car itself, and the driver will be getting out, rolling it out, and sitting there for a few hours charging. Now, we don't for a moment suspect that we're suddenly going to have a rush of people wanting to have hundreds of square meters of solar in the boot of their car to charge it and sit there for 4 hours in the sunlight. Again, this is a demonstrator project to show what the technology can do and really to drive discussion. So along with the solar, we also do other technologies using the same equipment. So the most advanced one is this. You can see a picture here of a printable biosensor. This is a glucose biosensor. The idea being that you can lick this sensor, stick it in a machine, and it'll tell you blood glucose levels. So the company we're working with on that, GBS, they listed on the NASDAQ at the end of last year. Just got a 12.6 million MMI grant to build the first functional printing facility in Australia, and it'll be right here at the University of Newcastle. So that'll be happening over the next 18 months, which is quite exciting. So all of these things, these demonstrator projects are really working towards commercialization of this technology. And we have a partner company now, Cardunia Energy, who's looking to commercialize the solar panels in particular. And the focus is really commercial roofs at this stage. There's 100 million square meters of industrial roof in this country that is currently not covered in solar. And the primary reason for that is the weight. So a standard solar panel is around 18 to 20 kilograms a square meter. When you start putting that on industrial roofs, you have to start spending a lot of money on reinforcing the roof to be able to take the weight. This particular technology does not have that problem, and that's where the commercialization of the product is going at this stage. So This started life in our laboratories 20 odd years ago, and they were 2 by 2.5 millimeters. We're now at pilot scale producing hundreds of meters, and in the next couple of years we'll be producing kilometers. So that was a whirlwind tour through printed solar. Thank you for your time, and happy to answer any questions.
Thank you very much for your fantastic presentation. As always, excellent.
Yeah, no worries.
There is a flood of questions on the app. However,
Okay.
we are in a tradition fashion. I'm going to open it to the floor. Amantas.
What's the organic molecule that is being used in these devices?
What is the organic molecule that's being used in these devices?
It depends on the project. So for the very, very low cost ones, we might use P3HT, which is a very, very standard bucket chemistry polymer. But some of the other molecules we're looking at the moment is PDC-BT and ITIC. So it depends on the application. We can roll in different materials.
What's the lifespan of the polymer? So, assuming it's UV stabilized.
Lifespan of the polymer. So the lifespan of the polymer is going to be longer than the device. So the polymers themselves are typically 7 or 8 years. The devices, we're probably looking at about 3 or 4 years lifespan. Depends on the barrier film that we use, because some of the interfaces break down before the polymer does. Even when you factor that in and factor someone coming along, getting on the roof, replacing it, you can still have the energy produced be as cheap or cheaper than traditional silicon.